Welcome to this explainer. You know, if there's one topic that absolutely terrifies students, it's probably quantum physics. But today, we're diving into a brand new paper by Dan Adrian German that totally flips the script on how we learn this stuff. It's called A Term-Rewriting Semantics for Pure Quantum States, and trust me, it's a real game changer. Let's get right into it.
So picture this. Can an average middle schooler calculate a quantum circuit? I know. Your immediate reaction is probably, no way, absolutely not. We usually assume you need like an advanced university degree just to survive the first chapter of a quantum mechanics textbook. But what if I told you that the answer, thanks to the research we're breaking down today, is actually yes?
Section 1, the quantum math problem. Because here's the thing. Conventional quantum math is basically a giant, terrifying wall for beginners. We're talking intimidating linear algebra, complex numbers, matrices. It is a massively steep learning curve. But the research we're looking at today proposes a totally different route. What if we just used simple arithmetic to describe the basics of quantum circuits? It literally bypasses that whole initial wall of complexity.
The author actually puts the main goal perfectly. To quote the paper, "The misty state picture is a good way of getting people to the heart of some non-trivial quantum theory without having to first absorb a huge amount of irrelevant math." I mean, hit the nail on the head, right? By skipping those early mathematical roadblocks, we can get first-time learners straight to the good stuff, the core concepts of how quantum computation actually works.
Section 2, enter the misty state. Okay, so let's define exactly what we're talking about here, just to ground ourselves in the actual terminology that Dan Adrian German uses. A misty state is defined as a term rewriting semantics for pure quantum states that relies on an elementary rewriting system to accurately describe quantum circuits. Now, I know that sounds like a mouthful, but in much simpler terms, just imagine taking these incredibly complex quantum states and translating them into a super straightforward system, a system where you're just rewriting terms step by step, following a really basic set of rules.
Now, this brilliant idea didn't just pop up out of nowhere. Back in 2017, Terry Rudolph first introduced this kind of elementary rewriting system, specifically to teach the basics of quantum circuits to high school and middle school kids. Fast forward to July 2026, and Dan Adrian German has published his new paper that takes those original ideas and dramatically extends them. We're talking pushing them into far more complex theoretical territory.
Section 3, simple math, universal accuracy. Here is the really clever part. The system calculates to a, quote-unquote, good enough accuracy using just a tiny universal set of gates. And it's important to note, this doesn't dumb the physics down at all. Instead, it leverages these really remarkable, heavy-dude mathematical results by Yaoyang Shi and A.Y. Kataev. So it's essentially running high-level math behind the scenes to smoothly approximate complex quantum states, which keeps the front-end experience for the student completely manageable. Which actually brings us to a really surprising number, 0. Yep, 0. That is exactly how much fundamental accuracy is sacrificed for first-time learners when they use this method. The author makes it absolutely clear that this misty formalism is universal. You can use it to do literally any quantum calculation. Okay, sure, you might have a slight overhead in the total number of steps you have to take, but the fundamental underlying accuracy of the calculation, it remains entirely intact. 0 loss.
Section 4, a bridge to advanced physics.
Now, a quick clarification from the author, because this is absolutely crucial. They aren't saying we should just toss out traditional math and recast all of quantum theory into this misty formalism forever. No, it's meant to be a pedagogical bridge. Step 1, you start with misty states and simple math. Step 2, you use that to gain a deep, intuitive, conceptual understanding of non-trivial quantum theory. And only then do you reach Step 3, which is transitioning smoothly over to the full, conventional quantum mathematical apparatus. Basically, it gets you in the door, shows you how the house is built, and then, once you're ready, it hands you the heavy tools.
Section 5, expanding the misty formalism.
So let's look at how German's paper pushes this teaching framework into entirely new territory. He actually extends it in 3 very specific ways. First, he successfully maps entanglement swapping. That's the wild phenomenon where particles become entangled even if they've never directly interacted. Second, he introduces a new category of irreducible misty states, which act as fixed points to really ground the math. And third, he tackles the GHC game, which is a famously complex thought experiment that explores the limits of quantum entanglement. And he does all of this within that same simple representational semantics.
I want to focus on that second extension for a second. Establishing a new category of irreducible MISTY states as fixed points, because it's particularly crucial. By locking in these fixed points, the paper essentially creates an entirely new general setting for representational semantics. It takes this basic framework, remember, something originally designed for middle schoolers, and actually gives it the robust foundational structure you need to handle truly advanced quantum mechanics.
This represents just a massive leap in capability. If you look at Terry Rudolph's original 2017 proposal, it was focused purely on making the basics of quantum circuits accessible to young students. But German's 2026 extension? It's successfully mapping highly advanced applications, stuff like entanglement swapping and the GHZ game, using this exact same foundational term rewriting system. It is undeniable proof that the MISTY state system scales upward beautifully.
Which leads us to a pretty fascinating final thought. Think about it. If quantum physics, literally one of the most notoriously difficult, mathematically dense subjects in human history, can be simplified this elegantly for first-time learners without sacrificing accuracy, well, what other impossible subjects are just waiting for their own MISTY state? What other incredibly complex fields are hiding behind massive walls of irrelevant math or jargon, just waiting for the right term rewriting system to unlock them for everyone? Thank you so much for joining me for this explainer. I really hope this helps you see the whole learning process in a completely new light.